Thanks for joining us. In today's webinar, we will be highlighting designing PCBs for the Internet of Things with constraint management for routing. Hello from sunny Central Florida here at RF Laboratories. My name is David Zima, and I have the privilege and pleasure of speaking today on wireless design and IoT or Internet of Things. For the past 25 years, I have enjoyed helping other developers of wireless devices to market by assisting in the design process. This has typically included design, layout, test optimization, and regulatory compliance. Today, I am excited to cover the exploding area of IoT development and one of its associated design challenges. Designing electronic products with IoT capabilities is no longer the exception, it is the rule. IoT technology not only opens up numerous new product categories of electronic devices, it drives innovators to rethink the ways that consumers interact with traditional techless products. From makers to startup companies and beyond, the opportunities to invent new tech devices and reinvent existing products with IoT capabilities, from health trackers to thermostats, are seamlessly endless. Electronic design is no longer just schematic capture and printed circuit board layout. The PADS product creation platform integrates many of the design tools needed for IoT designs. Leveraging the capabilities from Mentor Graphics, the largest EDA supplier for printed circuit board design, PAD Suites provides a range of capabilities from schematic capture and layout to simulation and analysis. And for specialized design requirements, there is a range of options available from DDR timing analysis, DC drop power integrity simulation, advanced high-speed routing, RF design, and advanced FPGA optimization, to name just a few. Since today's general topic is IoT, let's begin with a brief description. IoT stands for the Internet of Things. It has given rise to the demand for good RF design practices from the mains, from the wall outlet power, all the way to the antenna. It has also increased the need to understand what design requirements will comply with regulatory certification and what oversights may lead to failed tests at compliance test time at an FCC or CE lab. There are several IoT standards being employed today, from Zigbee, Z-Wave, to ANT, Bluetooth, and -7, as well as LoRa. In PCB layout, constraints involve just this: the state of being checked, restricted, or compelled to avoid or perform some action. So in other words, making a successful layout for a given design more likely by systematically limiting the design scope before we start. Design constraints set up in layout must start with the manufacturer's recommended design constraints. These are normally provided in an application note for the primary RF IC in consideration. The PCB stack buildup is a great place to start. Power traces with high-speed signal restrictions must be adhered to avoid undesired currents and noise. Current loop prohibitions and critical decoupling capacitor placement and routing are also important application note guidelines to follow from an application note when initially setting up constraints. Perhaps most important is a reference layout of all copper layers. This should be viewed as the golden rule when in doubt. All constraints should be configured with the end goal of producing copper layers as close to the reference example as possible. The manufacturer's app note will often include data collected analytically or empirically that shows important design and performance characteristics. Impedance matching in required areas of the design must be adhered to for optimal results, especially between the radio IC and antenna. More than one antenna option will be provided normally. The bigger, the better when it comes to antennas. But if space is an issue, a PCB trace antenna or chip antenna are alternatives. It is best to start with the antenna and work your way backwards to the IoT radio component placement and routing. Again, antenna, radio, and then the rest of the design is normally a good way to prioritize the pre-design and constraint criteria. A recommended stack build-up will normally be provided and should be followed with few exceptions. This will be one factor in many that determine the trace width and other impedance parametrics. It is important to remember that the data provided by the manufacturer in the app note is based on specific component selections, although there may be an inductor or capacitor value stated. Other component parameters can be marked effectively. The most critical of these are the components between the radio IC and the antenna. When looking at a well-conceived and executed RF layout, it is a thing of beauty, as we see here. More importantly, it is a very deliberate and self-conscious effort at constraining all design artwork to be devoid of pitfalls and strictly adherent to high-frequency design rules. I'm often asked how to make a successful RF layout. My RF layout tools have been mentor pads for over 25 years and more recently Pads Professional. The combination of understanding good RF layout practice, RF constraint implementation, and Pads Professional is a recipe for success and has been for me for many years. Firstly, some basic understanding is desirable to effectively use the PCB design rules we will cover today. It is then easy to identify the undesirable effects that can arise and how to avoid them. The reason PCB layout becomes more and more important is because of the trend to faster, higher integrated, smaller form factors and lower power electronic circuits. The higher the switching frequencies are, the more radiation occurs on the PCB. With good layout, many EMI problems can be minimized and meet the required specifications. So I'd like very briefly just to cover some of the constraint considerations for any RF layout. And some of the primary ones for PCB considerations during the circuit design are the board stack up, power and ground planes, decoupling capacitors, traces, vias, and other PCB components, clock distribution, which many of you may already be familiar with. But let's start with electromagnetic interference and electromagnetic compatibility. Electromagnetic interference, or EMI, is radio interference energy that interferes with the operation of an electronic device. This RF energy can be produced by the device itself or by other devices nearby. And EMC is electromagnetic compatibility. It's the ability of an electronic product to operate without causing EMI that would interfere with other equipment and without being affected by EMI from other equipment or the environment. So the very reason we're going through the effort of learning these rigorous RF practices and layout is because of EMI and EMC. Now, as I mentioned previously, this is a design that was done in Pads Professional layout, and we do have clock signals here. We have a crystal up here and another crystal down here. These clock signals are not being provided from a separate clock driver, but are actually integrated into the RFIC. And the time and frequency domain of a clock signal are significant design parameters. An important aspect is that in the frequency domain, the amplitude of the higher frequency harmonics depends on the rise and fall time of the signal. The longer the rise time, the smaller the magnitude of the harmonics. So this is something that really should be considered when we're doing our initial constraint setup. Also, among some of the very critical considerations for constraints for RF layout are the lengths of traces And really the question is if the lengths of traces are in the range of the signal's wavelength. Then the user has to consider the effects of transmission lines. The problem that a user must deal with are the time delay reflections and crosstalk. To get better understanding of these problems and where and how they arise, it's useful to know what transmission lines are. They are simply the traces on a PCB and depend on the length and the frequency of the signals passing through them. So even though we might look at this layout here, we have a transmission line here and also over this side that deal with the antenna and the radio frequencies. We also have transmission lines for the clock frequencies here, as well as perhaps high-speed data or differential pairs. All of them have to be thought of as transmission lines for our purpose. Another property of a transmission line is the characteristic impedance. And of course, 50 ohms is very common, if not the industry standard for an RF front end like we have here. If there are any other impedance changes in the signal chain, for example, if we have source and load impedance changes, we have vias or connectors between the source and load, reflections can occur, and these reflections cause over and undershoots from our desired result. Crosstalk is another parameter to consider, which deals with the mutual inductance of two parallel nearby routed traces. And one is called the aggressor. For example, we have some traces over here that are close enough where we could experience some crosstalk. One of these, if it had a strong signal, would be called the aggressor, and that trace would carry the signal. The other is called the victim. That trace would be influenced by the aggressor. And due to electromagnetic fields between the two, the victim would be influenced by an inductive and capacitive coupling. Now, in our discussion of constraint considerations, we also should mention differential signals. And in the case of differential signals, we have one here we could consider as an example. The negative effect of crosstalk is a positive one. The signals on each trace are, in theory, exactly equal in magnitude and opposite in their sign. So their electromagnetic fields cancel each other and the return current on the ground plane as well. To achieve this, the traces for both signals must have the same length so that the propagation delay times are equal. Next, we mention return current and loop areas. An electrical circuit must always be a closed loop. Up to now, only the signal path was discussed, but not the path back to the source. The return current, as it's called. With DC, the return current takes the way back with the lowest resistance. With a higher frequency, the return current flows along the lowest impedance, and this is directly beside the signal. The last general topic I'd like to cover today is time of flight. So TOF, or time of flight delay, gives you the ability to specify the time of flight based upon how long it takes the signal to propagate through the net. Length gives you the ability to set physical constraints that instruct the router to keep the net length within a specific range. There is a different TOF, or trace orientation function, which is for statistical prediction of printed circuit boards, radiated susceptibility and emission, but that's different than really what we're talking about today. Now, because many of the aforementioned items can affect transmission lines, EMI problems can occur. To reduce these problems, good PCB design is important, and with some simple design rules. The PCB designer can minimize these problems. A good PCB layout starts with the circuit design. Do not postpone considerations about the layout. One of the most important aspects affecting the layout is the location of each functional block. Keep their devices and their traces together. And we have an example we can look at actually right here. Here's a layout where we have functional blocks. The antenna switch block you can see in a purple outline. I'm highlighting the front end block here. And this is a way to group, and something that Pad's Professional I love about it. It really has been a great tool in grouping similar nets that have certain parameters that are similar, speeds, time of flight, and all of the items we had just covered. Now let's continue on and just talk about some pre-constraint questions that are really good to ask before we actually even go into our constraint manager, things we really should write down and have prepared so that our constraint assignments are very well understood and implemented. So one of the first questions I always ask is, what's the highest frequency and what's the fastest time in the system? Another is, what are the electrical specifications at the inputs and outputs of the sinks and the sources? Are there sensitive signals to route, for example, controlled impedances, like we looked at previously? Propagation delays on traces, clock distribution buses. Is there a microstrip that would solve a problem, or would we need to use a strip line and bury it? How many different supply voltages exist? And often those supply voltages can be put into different groups in the constraint manager as well. So does each supply voltage need its own power plane, or is it possible to split them? So with all these questions, where do you start? How do you begin using a tool like PADS Professional prior to constraint management implementation? Well, if you create a diagram with functional groups of a system, for example, transmitter path, receiver path, analog signals, digital signals, and so forth, like we've done here with some of our groupings, it really does make it a lot easier to initially assign the constraints. And are there any interconnections between at least two independent functional groups? And you have to think about crosstalk in those cases. You want to clarify the minimum width, separation, and height of a trace with the PCB manufacturer. What's the minimum distance between two layers? We covered that in our stack buildup. And what about the minimum drill and requirements of vias? Is it possible to use blind and bury vias? And would those choices be even permitted with your design, your target prices, and even if your board house can actually accomplish some of those mechanical requirements? I'd like to turn to the board stack-up just for a moment. If we go under our Setup and Stack-up editor, we'll see a basic tab that allows us to look at our board stack-up. Now, this might not be considered a constraint, but it's a very good place to start to determine the right board stack-up. But fundamentally, there's really no information about how many layers should be used and how the board stack-up should look. Generally, the use of microstrip traces need to be at least 2 layers. And in this case, we have 4 layers. Our primary layer, copper layer, and our ground right beneath it, with power and our layer 4 beneath that. One of the other questions we ask when we look at board stack-up is to find the location of each section of the board by means of the functional diagram. Try to keep the devices together to avoid interaction. And we looked at that right here, where we had different groups of components. So our board stack-ups are a really good place to start, and it's necessary in high-speed designs to have at least one complete ground plane, like we have right here on layer 2. So we also want to remember to use microstrip traces for sensitive signals. With a complete power plane as close as possible to the ground plane, it's possible to create capacitive coupling between them to get low impedance at high frequencies. This reduces the amount on small decoupling capacitors at the power pins of the devices. The closer the planes, the less impedance is present. So as I mentioned previously, a complete ground plane in high-speed designs is really essential. Additionally, a complete power plane is recommended as well, like we have here. And the best solution would be for every voltage to have its own layer and its own ground plane. But of course, that can be very expensive, and we would have a huge number of layers if we did that. Now, moving on to decoupling capacitors, as we mentioned, we have them right around here, around the periphery of the RFIC. Decoupling capacitors between the power pin and ground pin of a device to ensure low AC impedance to reduce noise and to store energy. So to reach low impedance over a wide frequency range, several capacitors have to be used. That's why a real capacitor consists of its capacitance and its parasitic inductance and resistance. So therefore, a real capacitor behaves as a resonant circuit. We don't think of it as such, but it really does. The capacitance dominates and the capacitor acts as an inductor here. With the use of several capacitors with different values, low AC impedance over a wide frequency range can be provided. And that's why often in RF designs, IoT designs like the SLAR design, we see two or more capacitors in parallel to obviate those high frequency noise issues. Now, moving on to traces, vias, and other PCB components, the use of vias is essential in most routings, but the designer has to be careful in using them. They add additional inductance and capacitance, and reflections occur due to the change in the characteristic impedance. So vias also increase the trace length. So we have a constraint option in PADS Professional here. If we click our constraint manager, which is already open, and I'm just looking at this one net we have here, it's called RF 900 megahertz. We have a via assignment option where we can just select, we can actually assign a via that would be appropriate for this particular RF trace if we had to go from one layer of the board to the other. Now, it's also important to remember that when we are looking at a design like this, if we go back to our finished layout here, that right angles in a trace can cause more radiation. The capacitance increases in the region of the corner, and the characteristic impedance changes. So this impedance causes reflections. So we want to avoid right angle bends in a trace and try to route them at least with 45-degree corners to minimize any impedance change. Best routing would be a round bend like we see right here. So you want to separate high-speed signals from low-speed signals and digital analog signals. For example, by going at 90 degrees instead of parallel. And to minimize crosstalk, doing the same. So avoid vias in differential traces like we have here. If it's not possible to avoid them, then use vias in both traces or compensate the delay also in the other trace. And finally, I'm just going to mention briefly clock distribution. Clock distribution and clocknet should have minimal delays. And here we have a very, very tight and direct routing with a crystal and an oscillator, all part of the RFIC, both for the low frequency up here, 32 kilohertz, and the 32 megahertz clock down here routed to the BGA. You want to reach low skew and implement delay time compensations if you do choose to use an external crystal driver to a part like this, which is not very common with this type of RFIC. But you want to, above all, avoid branches to reduce reflections. Use a clock driver to distribute the signal in every device and consider proper termination. As we conclude our discussion of constraint implementation for routing RF PCB layout, I would like to acknowledge the following resources that I have referenced and cited. Mentor Graphics RF Solution Guide, Mentor Graphics Constraint Manager User's Manual, and lastly and finally, TI's High-Speed Layout Guidelines. So this brings us to the end of my presentation. Thank you for your attention today. It was my pleasure sharing some of my ideas on RF layout techniques with my tool of choice, PADS Professional Designer and PADS Professional Layout.